let's get in with the material for today. So far we have been talking all about forces, right? Our lecture last time brought on how we're going to be dealing with all these forces. You know, every single time we had talked about motion so far, we'd been talking about how things moved. Position, velocity, acceleration, the time between steps of our process. We had all of these things together to describe exactly how something would move. We could plot out its path, we could find its trajectory, we could do all sorts of things with it, but we never really had an answer as to why. And why was there some sort of acceleration or anything? Well, I said gravity, and we just kind of accepted that because, sure, we know what gravity is, but there can be more than just gravity. There can be a lot of different things going on at once. Sometimes it was a rocket attached to a hockey puck. But all of those things we said provided an acceleration, but we didn't talk about why, and the reason why was because of force. So, looking at all of this stuff, we have Newton's second law here, F is equal to ma, but essentially, any time that we are looking at an object that has forces acting upon it, we can find the acceleration because of those forces, but the process, first, we take every single force acting on an object. If I take my mug of coffee or anything else and I lift it up and I push on it with this finger and everything else, I have a force holding it up. I have my force from the other finger pushing it. I have gravity pulling it down. I have all sorts of different things acting on it. But if I take every single one of those forces and I sum them all up, and I have to do vector addition here because remember, force is a vector, but I sum up all of those forces into one term that we call F net, then we can take F net, divide it by the mass of the object, and we have the acceleration. So this is like another additional step to all of our kinematic solving, right? In kinematics, if we are interested in a final position or a final velocity, we took all of the information that we had and we summed it all up together, right? And maybe you had to solve out for some things like time, but now we have this additional step. If we don't already know the acceleration, but we do know the forces, now we have this extra intermediate step to find acceleration, to find everything else we're used to finding at this point. So, because force is a vector, we might remember that anytime we have vectors and we are trying to add vectors together, the best way to do that is to sum up all of the x and y components of each one of these. So F net, being its own vector, is going to have a total x component, a total y component, and that is just the individual components of every single constituent vector. So, when we do that, we might end up in some special cases. One of those special cases is what we call equilibrium. And even then, that gets a little bit more specific, whether we are looking at static equilibrium or dynamic equilibrium. All in all, it doesn't really matter which one we are in. If we are in equilibrium, the net force, and therefore the net acceleration of the object is zero. But specifically, if we wanted to look into those, a static equilibrium, static means stationary. So that means no velocity, which is a constant velocity. Acceleration is equal to zero. In a dynamic equilibrium, we have a non-zero velocity, but it's constant and our acceleration is still zero. So realistically, how the forces behave between either of these two cases, no real difference. Net force, still zero. But the way that we approach these things, when we know that the net force is supposed to be zero, then we also know that all of the x components and all of the y components should also sum up to be zero. So our problem-solving method for all of this stuff, remember, and I kind of have these in order, but sometimes I break this order myself. We want to draw a picture. We want to think about all of the variables that we've got. We want to put all of our forces on the picture. Label the axes, draw the free body diagram, all of that good stuff. Please, it is not just an extra step for the fun of it that we draw these pictures. I still draw the pictures when I solve problems, right? I have been doing this for a long time. I still draw the pictures. That should tell you something, I would hope. But you want to draw the forces, you want to draw the free body diagram, you want to label your axes, you want to do any more physics, which is oftentimes writing down those kinematic equations. You want to do the math, which is the algebra, and plugging in the numbers. And then, of course, by then, we are having a good time, so we keep having a good time by tackling the next problem. So, some of the common forces that we have seen, and we talked about some of these last time, but of course, our first one would be weight, which is the force that we feel from gravity. I am on Earth right now. I feel a gravitational pull from Earth pulling me downwards. That force, I call it big F of g is always equal to mg. A normal force is any time I have two objects touching each other. That is, if I'm sitting in my chair is pushing back up on me with a normal force. If I lean over and press against the wall, my wall is providing a normal force. If I lift up my mug, I'm providing a normal force. Anytime you have contact between two objects, there is a normal force between those two. And the entire point of that normal force is that the two objects that you have, my two hands, for example, do not press into each other, right? There is a boundary between those two. We can still distinctly see my two hands. They're not fusing into one. Two separate objects cannot just phase into each other. They have to stay separate. The normal force is what keeps them separated. One thing I didn't touch on very much last time that we're going to hit a little bit harder today is what a scale would measure. If you stand on a scale and it tries to tell you about your weight, it might not always be accurate like we expect it to be. See, what it's doing is not measuring the gravitational force. It's measuring how much it needs to push back up on you for what it assumes is a gravitational force. But imagine something like this. I used to have a very finicky, very mean cat. To get him to stand still was impossible. But sometimes, for whatever purposes, we would need to weigh him. So making him stand on the scale himself was impossible. What I would do instead is I would stand on the scale, I would get my own weight. Then I would pick him up and stand on the scale with him. The scale, I'm touching the scale. It's supposed to be measuring my weight. But once I'm holding the cat, I've got, and this was a massive cat, an additional 20 pounds. And he wasn't super fat or anything else. The cat was just a monster. He was huge. It's a terrifying beast. That additional 20 pounds is not 20 pounds of me, though. My pull, the amount of pull that I'm feeling from Earth has not changed. What has changed is that now I have to be providing a normal force for the cat. The cat is pushing down on me. That additional push down on me means the scale needs to push up even more, and it thinks that I have gained that weight, while in reality, I'm just holding something else. In an opposite kind of scenario, imagine you're standing on a scale, and you have a friend on each side, and they kind of grab your arm and lift you up a little bit. What do you expect the scale to do? Any guesses on that one? The scale thinks you'll weigh less. It's not that you do weigh less. You didn't lose any mass because somebody helped pick you up a little bit, right? And they don't even have to pick you up all the way. They just have to do a little bit of a lift there, a little bit of force upwards. The scale doesn't know the difference, whether or not I have more or less mass. The scale is only trying to tell us what the normal force is. So when we're talking about the weight that we feel, what we're actually talking about is the normal force that we're feeling. Does that normal force take away from one's weight? No. The normal force is what we feel as the weight. Right? If you are walking upstairs or anything else, what you're really feeling, you're feeling a little bit heavier than it takes to stand normally. Right? There's an additional force from your legs because not only do you have to support yourself against gravity, but you also have to lift yourself up the stairs. So the weight that you feel on the stairs, the extra strain on your legs, is because you have to be accelerating yourself upwards. So keep that in mind. We have a few of these problems that deal with this, how much weight do we feel? What would the scale read? The scale is not reading our pull up from gravity. The scale is reading our normal force. So, two other forces, one of which we have seen now, one of which will be brand new for today. First, of course, is tension, right? We saw tension last time with the ring that had 3 ropes attached to it. Anytime we have a rope, string, chain, wire, I guess, don't hang things from wires, tension is involved. Tension is never a pushing force. There's one thing that imagine here, if I'm trying to pull something with a string and I try to push, it doesn't push. The string only pulls because that's when it's taut. If I try to push with the rope, then it just goes slack and collapses and doesn't do anything. So tension always pulls, and it pulls at each end that it is touching. So if I have a rope between my person and the block, tension pulls this way, tension pulls this way. Tension pulls on the person and pulls on the block. Anywhere it is connected, it is pulling with the same tension. Now, the last one, the new one, the more complicated one, arguably more complicated than anything else we have seen so far, is friction. And let's talk about why. Friction is a force that tries to prevent movement. That is to say, if I have some sort of block that already has some velocity, friction is going to say, no, none of that stuff. I'm going to pull this way. If the block were moving in the other direction, friction would flip. Friction always opposes the motion. But you might notice here we've got two different sets of friction equations, but both of them have the same general shape. We have this lowercase f, which is what we use to represent friction. We have it usually, or kind of, equal to mu times lowercase n, which remember I write that as the normal force. So let's try something. If everyone would be willing to participate here, and I'm not going to ask you to come on camera to prove it, but this is a good little way to check something. Take your hands, rub them together like this. Don't put a lot of force into it. You might feel a tiny little bit of heat, but probably not too much, right? I don't feel really any difference between doing this, my crazy dance moves, versus when I push my hands together. Maybe there's a little bit, but not much. So once we're used to that, now start pushing a little bit more. I don't know if you guys can hear that, but there's now a fair amount more friction between my hands, right? I have to push a bit more to actually get my hands to move back and forth. If I get really crazy with it, my hands have a really tough time. And when I'm doing this, for one, I can really tell, I can feel it in my arms that I'm using a lot more friction, or I'm using a lot more force to overcome this friction, but also I can feel the heat in my hands. Right? The heat in my hands tells me there's a lot more friction there. Friction is going to generate a little bit of heat, and we might have experienced that at some point throughout our lives. But that extra heat says there's more friction there. That more friction there is not because my hands have changed. It's because the normal force between my hands has changed. Each hand is exerting more force on the other. That increase in the normal force means that so too did the friction force increase. So I want you to keep that in mind as we deal with a lot of these things. We have to be aware of what that normal force is doing. We have to be aware that as we increase or decrease the normal force, whether that be lifting something up against gravity or pushing against a wall, anywhere that we would have a normal force, there is going to be friction based on that normal force. Normal force affects friction if an object has more mass. Not necessarily. It's not based on mass, right? Because the normal force does not need to be based on mass. If I push on the wall, the amount that I push on the wall doesn't, in a very indirect way, but it doesn't really depend on my mass, right? That has nothing to do with gravitational pull or anything else. That's just how much am I pushing into the wall. But in the same way, if I try to slide against the wall and I'm pushing with a lot of force, the friction is going to be greater between my hand and the wall. And I love to use the wall because this is an example. The wall does not care about gravity, right? This is straight up and down. Whereas the floor, there might be some argument of gravity there. So the other part of this, though, normal force is only half of the equation. Of course, the other part is what we call the coefficient of friction. And the coefficient of friction is some value between 0 and 1. It is essentially a measure of how rough or how much two objects will stick together, two surfaces as they stick together. What is the normal force of the second graph? You mean this one right here? Okay, for that one, we don't have the normal force written out here, but if I was to do this, in this case, I would expect my normal force goes like this. Gravitational force goes like this. The two of them would be equal in magnitude. which oftentimes we will see the normal force is equal to F of G, but that is not always the case. So, when I'm talking about this coefficient of friction, though, this coefficient of friction is always some value between 0 and 1, and it is a measure of how much those two surfaces will stick together. So the higher it is, the more sticking something actually is. For example, rubber on asphalt is very nearly a coefficient of 1. It is a very high friction coefficient, and that's generally the reason why you can't skid tires very easily. It takes a fair amount of force, right? Anybody that skid tires or anything else, you could really only do that if you're already moving fast and you really slam on the brakes. Most of the time, it doesn't do that very well. On ice, very different story. Rubber on ice has a fairly low coefficient of friction, and that's why it's a lot easier to accidentally start sliding in winter weather like this. So for any of these things, as we're looking, what we really have is we're looking at, on the microscopic scale of something, imagine a block, a sanding block, right? So it's a wooden block that's got some sandpaper along one end. If we look at it from a distance, that thing is mostly flat, mostly straight. If we look very closely, though, there's all of these tiny, like, microchasms and everything else on this thing that when you actually touch it, you can feel that roughness to it. The more roughness something has, the higher coefficient of friction it's going to have when in contact with something else. Because friction is those microchasms getting stuck together and pushing up against each other. So two completely smooth things, like if you are skating over ice or something. Ice, very smooth, very low coefficient of friction. Asphalt, rubber, not very smooth things. They bite into each other very, very well. So in this case, as I have friction written, I haven't specified whether I am talking about static or kinetic. And that's an important distinction. So take the names of these things kind of exactly at face value. A kinetic friction is a friction that we feel when we are already moving. Kinetic. And it's an easier expression because it's always equals, right? F sub k, kinetic friction, is equal to the kinetic friction coefficient times the normal force. If we look at the case of static friction, now we're in a little bit of a trickier situation because static friction is less than or equal to that coefficient times the normal force. So let's think about something for a minute. If you have a desk or a chair or anything else like that, I might take my book, for example, the textbook that I've got laying right here. Let me take this thing, and I'm going to give it a little tiny bit of a push. And you can see just the corner of this thing. I am giving this a little bit of a tiny push. Would you argue that I am exerting some force on this thing? That wasn't the book. That was something else. If I'm pushing on this thing, but it's not moving, surely there is another force acting, compensating for my force pushing back up against me that is stopping the book from moving. That is static friction. If I push too much, if I overcome that static friction force, then indeed the book does start moving. But until then, friction opposes my movement. It stops me from moving. And that's why it's static friction, because it is up until the point that something starts moving. Static friction is there, but it's a reactive force. That is to say, it is not pushing with its full force mu times n back at me, because then it would be sliding like this. Instead, it is only canceling out what I am doing. That is why it is a less than or equal to force, because it is only there up to a limit. It is only there up to a limit, and if we exceed that limit, then we start moving again, but friction will only provide enough force to make sure that we don't have any net motion until we exceed it. Doesn't normal force take away from gravitational force? It doesn't take away from gravitational force. They are counteracting each other, but both of them are still there. There's nothing I can do to get rid of gravitational force aside from getting rid of mass. The only way I can get rid of gravitational force is to get rid of the mass. Otherwise, gravity is still going to be pulling down, but I might have other forces that help cancel out that pull. It's not that it goes away, it's just that there are other things also acting. Net force is 0 when an object is static? Not necessarily, because remember, in a dynamic equilibrium scenario, we might still have a velocity. It's when we have 0 acceleration that we can say that the net force is 0 and is static. Well, 0 acceleration, 0 velocity, that is the true static scenario. If it is still got a velocity, then we are looking at our kinetic case. If you were in a frictionless environment, would you have to push with a force greater than the object's mass? No. Any amount of force in a frictionless scenario, any amount of force would start you moving, because there's nothing to oppose your motion. It's just any time I would have a force, if I have a very large mass and a very tiny force, I would just end up with a very tiny acceleration. That's the whole concept behind things like solar sails. Solar sails are essentially trying to take the force from the solar wind and use that to propel a large spacecraft. The large spacecraft has a lot of mass comparatively, and the amount of force that we're going to feel from the solar wind is very tiny. But because there's no friction, there's nothing to take away from that movement as we try to collect it. Then we get this net movement over time. We have a very slow acceleration, but because we expect this trip to take years and years and years and years and years, it's not a big deal if we take a very slow acceleration, because we have already planned for that. We're going to get there when we do. But it's all about that fuel efficiency at that point. So, we've had a lot of great questions so far. Is there anything else that we can hit on for this that I can help clarify before we dive into some of our problems? So the reason that I'm pulling that one up is, let me look at the exact wording on this one. I'd worded this in a very specific way that I tried to imply something. Generally speaking, almost always, the coefficient of static friction is greater than the coefficient of kinetic friction. So when I'm talking about something that is going to be moving, if it's the same object and it's going to be moving here, I'm just trying to pull up the exact wording, the largest friction force is likely going to be a rough surface. Make sure that I'm not just crazy here. A rough surface with just short of the force to actually move it, because if the coefficient of static friction is higher, then we can essentially get up to a larger value. In either scenario here, what we would have, if we could imagine that we are just shy of this maximum force, it looks something like this versus something like this. Imagine the scenario that we are in, essentially a maximized case, where we are almost exceeding that static friction force. Mu of s is almost always greater than mu of k. And the only time that it's not true is when they're equal. So since the static friction force is always greater than the kinetic friction force, or the coefficient, I should say, since the static coefficient is always greater than the kinetic coefficient, I would still expect there to be more friction force in the static scenario than I would with the kinetic scenario. Does that make sense? Okay. So yeah, that is the typical relationship that we're going to see, that the static friction is almost always. I am trying to think, there are very, very few scenarios where that's not true. And I guess the only thing that I would expect is maybe rubber on asphalt, where they're both 1. But there are almost no scenarios where they're equal. It's almost always static is greater than kinetic. So for the question 3, if I'm looking at the equation for friction force, force is equal to mu k times the normal force. There is not any dependence on what speed we are going through. And that's why I specified a block moving across the surface. It's already moving, so it's not that it wasn't moving and then it was moving. It was already moving. There is no speed dependence of the friction force. But to kind of go along with some of these descriptions, if you have moved large furniture, if you have tried to slide anything across the floor, you might have a little bit of personal experience in the fact that it's much easier to keep something moving than to let it stop and try to get it moving again, right? You require so much force to get this thing moving, but also at the same time, you have to be careful because sometimes it slides too much suddenly. You're putting a lot of force in and then suddenly it lurches forward because you have overcome that static friction force, but the kinetic friction is much smaller than that. So you get this sudden burst of acceleration, maybe when you weren't expecting it. And that's why it's so hard to control, but it's much easier if we can keep that thing moving. Is it possible that friction is greater than 1? The coefficient? No. The coefficient maxes out at 1. Okay. Yes, just mu. So I can have any force for friction, but the coefficient maximizes at 1. Let's try a problem here. And this is not a friction problem. This is more of a net force and normal force and all of the stuff like that kind of problem. Let's imagine here. Zach, mass 80 kilograms, standing on a scale in an elevator descending at 10 meters per second. The elevator takes 3 seconds to brake to a stop at the first floor. So it's moving downwards and it decelerates to a rest. Before it starts decelerating, what is the reading on the scale? Second, once it starts decelerating, what is the reading on the scale then? Draw a picture. Draw a free body diagram. Label your axes, please. Then, in 4 or 5 minutes, we're going to take a look together and see what you got for some of these values. So, go ahead and get started on it. All right, so I think I would like to start taking a look at this. But I do have one thing that I meant to announce towards the beginning here. This is not necessarily related to the course. Right around noon, I sent out an announcement. I have been asked to forward a message from our very own Physics Education Research Lab. So we have a Physics Education Research Lab in Krieger. We study how you guys learn physics. It is, we do a lot of collaboration with other groups. A lot of our decisions about how we teach a lot of our classes are based on the science that they find and the science that they kind of conglomerate that other groups have found and then they suggest to us. It's a wonderful thing. We do very much care about how you guys are learning this stuff. We are trying to give you the best chance possible to learn this stuff as well as possible. And a lot of our decisions in that are informed by essentially what we find from our results of the study. So within that message and everything else, our person coming from that lab currently is explaining what the situation is, what we're trying to go for here, and they have a survey linked in that announcement. So I would very much appreciate if you go through and participate in that stuff. It is not worth any credit. There is no penalty or anything else if you do not do that survey. There is nothing tied to the class for that survey. But you are all STEM students because you're taking a physics course right now. Whether or not you're actually in a STEM major, you are a STEM student right now. And we are interested in your opinions, your experiences, and everything else within learning physics. So do me a favor, do the department a favor, do the university a favor. Participate in that survey, participate in that study. We can find some more information. We can keep making these classes better and better for you guys. But that's my small plug on that one. You can find that in the announcement if you're looking for it, or you can send her an email if you have any more questions or anything else before you'd like to participate. For now, let's go ahead and dive into this stuff as we've got it. So, first things first, we draw our pictures. We always draw a picture. It's a big, important step. So, what I'm going to do here is I'm going to draw our elevator. Bam. And here is Zach. Bam. We've got all that good stuff. Okay. So from the very beginning, we know that the elevator is moving downward. So I'm going to draw like a dotted light gray vector, V naught, just to really imply here, hey, we have a velocity. Hey, that is not a force. Do not confuse it with a force. That is another type of vector. Everything else, I expect to see two forces here. What forces do I expect to see acting on Zach right now? What do we think? Gravity, I would agree with that. I assume this elevator is on Earth, so there should be a gravitational force pulling us down, and a normal force from the floor acting on Zach. I would agree. Any other forces? I wouldn't think so. He's not moving. There's no worry about friction or anything. Tension maybe for the elevator itself, but there's not any ropes attached to Zach right now. I assume nobody is like bullying him in the elevator and pushing him around. So I would argue that these are probably the only two forces acting on Zach. Tension and all that other stuff is going to be acting on the elevator box itself, but we're just interested in Zach. So let's start with part A of this problem. In part A of this problem, we are simply given the mass, the velocity, and right now we are before we have started accelerating. So let's do this. Before slowing. Before slowing, do we have any acceleration? No. We're moving at a velocity, and we're just going to cruise at that velocity. No acceleration. What does that mean about the net force? I'm going to do my triple dots. That means, therefore, no acceleration, therefore, net force is equal to 0. And while I'm here, I should not forget to draw my axes. I'm going to call this y. I don't really have an x direction. We can label it here if we really want to. Maybe the bully is pushing Zach from, in the negative x direction or something. But we don't have anybody else in this elevator or anything else right now. So F net is equal to 0. I'm only looking at forces acting in the y direction because those are the only forces that we've got. That means that if I were to look at every single force in the y direction, they should all sum up to be 0, and we look at the forces acting in the y direction. I have a normal force. I have a gravitational force pulling me down. That's it. Therefore, what the scale would read if we were looking at the scale, being the normal force would equal mg. This would be accurate, right? No difference in that whatsoever. Plugging those numbers in, we should find something like what? I think 784 newtons. Yes. That is the force that the scale would read when we start. Yeah, the 3 dots mean therefore. So acceleration is equal to 0, therefore net force is equal to 0. It's our fancy little proof language. I'm terrible at proofs, so maybe I shouldn't use proof language, but I like the 3 little dots. It's a lot easier than writing therefore. And sometimes I get tired of writing my arrows in every direction. So how do we feel on this thing so far? Do we all agree? So, going from here. Now, we're looking at the case where we have started our deceleration. So what I'm going to do here is I'm going to say now before slowing, during slowing. And let's do this in a light blue color so that we know it's a little bit different. During slowing, let's think about what happens. I have an initial velocity of, and I'll even do this as a vector, negative 10 j hat meters per second squared. What about my final velocity? What do we know for that? Final velocity 0. So, what direction is our acceleration going, up or down? Left, right, in, out of the page. What do we think? Any guesses on that one? I guess I can answer. Yeah, acceleration is going upwards. Acceleration going something like this. And again, I have drawn this as a dotted line on the side, not attached to Zach, because I want to make sure that I specify that this is not a force. This is something else, some other type of vector. I do want to include it on my picture because it helps me visualize what's going on, but it is not a force. And we say this happens in a time span of 3 seconds. So let me start from that. This sounds a lot like kinematics. Initial velocity, final velocity, time, acceleration. I have one handy equation that ties all 4 of those variables together. It is, of the 3, my second kinematic equation. It says, hey, final velocity is equal to initial velocity plus acceleration times t. There are other equations that would talk about my final velocity. For example, Vf squared is equal to V naught squared plus 2a delta y. However, in this equation right here, I don't have any idea what delta y is. They don't specify how far we go down when we're decelerating like that. So I'm going to say, nah, this is not a good one. I'm not going to bother with that one because then I would have to find delta y first, and much more work than I feel like doing. Instead, this equation that we have down here, I know V final, I know V initial, I know the time. I can find from this equation that the acceleration is equal to 3.33 meters per second squared. Right? Now with that, I can say, okay, well my acceleration must be from a net force acting on Zach. I love the engine sounds in the background. Thank you, neighbors. I don't know if that actually comes over the mic. I'm so sorry if it does. Yeah, it certainly does. We'll try and turn down that gain a little bit and see if that helps. So let me look at all of my forces going in the y direction. Now, what I'm going to say is all of my forces in the y direction do not necessarily equal 0. Now it's going to be m times a of y. Whatever acceleration I have, hint, 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 that is because of the net forces that are going to be acting on this thing. Those net forces being, well, the same forces I had from before. F of n minus mg. There's not any new force acting on me. It's just the same 2 forces as before. It's just now my net force must be equal to mg plus ma. So, and this is why, if you've ever like messed around in an elevator or thought about like those experiences you feel, think about this a little bit. If you get in the elevator, you close the doors close, you know, you hear it start to move. As it starts to move, you feel this slight buckle in your knees, right? Not a lot. It's not a huge downward pull, but it's just a little bit that you feel it. Versus when it stops, when it gets up to that top floor, when it decelerates, you feel just like a little bit of a lurch upwards. Just a tiny bit, not a ton. That is what's happening during these scenarios. That normal force has either decreased a little bit or increased a little bit depending on your net acceleration. So when I actually plug these numbers in to calculate everything out, I should get something like 1050.4 newtons. So when our acceleration is pointing upwards, the normal force has to provide a little bit of extra oomph to make sure that we actually accelerate in that direction. And we end up with that. The 3.33, this comes from my kinematics. I know some details about my kinematics here because I can say that I know what the initial acceleration, or I know what the initial velocity is. I know what the final velocity is. I know there is a time difference between those two states. There must be an acceleration between those two. I can solve out for what that acceleration is by plugging in these 3 variables. This is a scenario, most of the time we are going to find acceleration from our forces, but this is one of the times where we're going to find the forces from acceleration. We already know how the object moves. Now we're kind of exploring why. What forces go into that? Let's keep diving into it then. I've got another problem here, and it's a little bit fun. Our favorite power couple, Bonnie and Clyde, are sliding a 300-kilogram bank safe across the floor to their getaway car. There is friction here, right? That is a big deal. The safe slides with a constant speed if Clyde pushes from behind with 385 newtons of force and Bonnie pulls with 350 newtons of force. What is the coefficient of friction between the safe and the bank floor, knowing all of these details? Now, first step, of course, draw a picture. Please, please. Draw a picture, put all of your forces on it, label the axes, all that good stuff. If you'd like, what I'm going to do, I'm going to call the force from Clyde F of C and the force from Bonnie F of B. Just that way I can keep everything symbolic on my picture and keep it nice and clean. Helps me understand what's going on there. But what I want you to do, draw out this picture. Try to solve out for this coefficient of kinetic friction because the safe is moving. Take the next 5 or 6 minutes to do that, and then we will come back together and see what you got. Okay, so let's start taking a look here. First things first, we are going to draw a picture because that is always one of our first steps whenever we're facing these problems. If you are organizing some of your variables ahead of time, that's okay, but I want to see a picture immediately after that. So here's our level ground. Let's draw the safe sitting on that thing. Let's add some details. Let's make sure that we know this thing is the safe. It's got this. It's got the big spinny thing on the front with the little spindles coming off of it. Make sure that we know that we're talking about a safe. So that way, when we come back to our picture sometime later, if we want to look at our notes, we remember, hey, this is the safe problem. Even put some hinges. There we go. Fantastic. So we've got a complete picture of our safe. Now, I want to start drawing forces on this thing. What forces do I have? What do we think? Even if nobody was here, even if the safe was just sitting in place before the robbery, what do we expect? Gravity? I would absolutely agree with that. A normal force from the floor? I would agree with that. Anything else? Is there any other forces before anybody tries to rob this? Would I expect to see any other forces acting on this safe? Trying to bait someone into saying this, why don't I expect to see any friction? Why wouldn't I see friction? I'm sorry, I try not to bait out those answers too often or anything else, but sometimes in contexts like this, I do want to bring that up. I don't expect to see any friction because remember, friction is reactive. Friction is not a big deal unless something is trying to move the object. So right now, nobody's trying to move the safe. If nobody's trying to move the safe, friction doesn't need to do anything. Friction is only there to resist movement. Without any effort for movement, there's no need for friction. But we do indeed have somebody trying to move this thing because somebody's trying to steal the safe. So if I'm drawing these other forces that I would have the force from Bonnie going like this, and that's not very horizontal, but let's try a little bit better. That's a little bit more horizontal. So I would say this is my force from Bonnie, and I know this is incorrect. I know this is kind of sacrilege, but because I know Clyde is pushing on it, sometimes I like to draw my force like this. This is my force from Clyde. I know, technically speaking, the force should be on the other side, and if you drew the force from Clyde over here, that is totally fine. That is more correct than what I just did there. But the picture in my mind of what I'm expecting to happen here, I think I like this one just a little bit better for myself. If you disagree with this, not a big deal at all, right? However, so now the last thing that we need, this thing is moving, according to my picture, to the right in what I will call positive x. Friction, not very happy about that. Friction will oppose that motion and point in the opposite direction like this. Kinetic or static? What do we think? Kinetic, and I would agree with that because right now we see this thing is indeed moving with a constant velocity. So I'll label that in light gray to say, hey, that thing is there, but it's not one of my forces. So I've got a lot of these things. Now let's start organizing them a little bit more. Let me erase just a little bit so I got some more space over here. Oh, in black, please. Thank you. Of the forces and the different variables, rather, that I'm given, I have that the mass is 300 kilograms. I know that the force from Bonnie is 350 newtons. The force from Clyde, 385. What other variable do I know that I don't have listed on here? Friction is the one that I'm a little, well, not quite friction, sorry. I jumped the gun on that one. I wouldn't say gravity or normal force necessarily. Let me get to those in a minute. G and gravity is kind of included, wrapped up in that. There's one other variable, not a force. My big key to this thing, related to velocity, that's warmer. What I'm really thinking about is my acceleration. Since the safe is moving with a constant speed, we are in a case, not that one, of dynamic equilibrium. That is to say, the net force acting on the safe right now is 0. That's a big deal. Find that coefficient of friction. So now what I'm going to do, I do have forces in the x, I do have forces in the y. I know the acceleration as a whole is supposed to be 0, despite the fact that it's moving. Because the velocity is constant, there is no acceleration. So let me start with that. Let me say every force in the y direction to begin with. So if I sum up every y component, I would expect them all to sum to 0. And I look at the forces acting in the y direction. I see the normal force, I see gravity. Those are the only two. The normal force goes up. Gravity pulls down. Perfect. Next, let's sum up all of the x components. I'm really bad at drawing those capital sigmas. I, again, expect this to be at 0. I have f of b going in the positive direction. I have f of c going in the positive direction. I have friction force pulling in the negative direction. I know what kinetic friction is. I know that there is an equivalent I can plug in for that immediately, so let's do that. Take this a step down, or not even that. Let's just do equals f of b, f of c, minus coefficient of friction times the normal force. We're looking for the coefficient of friction. We don't know the normal force, but we can find it if we go back up to our y equation. So let's do that. 0 is equal to Fn minus mg. Add mg to each side, and I get Fn is equal to mg. Not always true, but often. Plug in that expression down here. That is 0 is equal to Fb plus Fc minus mu k mg. So remember here that I can have movement and no acceleration. It just means that I'm moving at a constant velocity. Constant velocity, no acceleration, no net force. All of the forces are balanced to keep this thing moving exactly as it is. That's Newton's first law. An object will keep moving or it will not move unless there is a net force acting on that object. So we're after mu of k. Our expression has all variables that we know are given or are constants. Solve out for mu of k. For a final answer, mu of k should be equal to Fb plus Fc divided by mg. If we plug in all of our numbers together, we should find a final result of 0.25. And that's it. Okay, mu k mg minus... So that comes from, if I look at all of my forces acting in the x direction, I'm just going to pull off everything that is acting in the x direction. I'm going to sum up every single one of those things all together. I have f of b pointing to the right. I have f of c pointing to the right. Both of those are pointing in my positive x direction. So when I come to my equation, I expect them both to be positive, positive. Friction, pointing to the left because it always opposes the motion. If my velocity is going to the right, my friction is going to the left. If my velocity is going up, my friction would be pointing down. It always opposes the motion. So that one's going to be minus. Then because I know it's a kinetic friction, in my kinetic friction equation, I always have that kinetic friction is equal to mu k times the normal force. From there, we said, okay, well, we know that we can plug that in, mu k times the normal force, but I don't necessarily know what the normal force is. So I had to go back to the y equation, and I had to say, okay, well, is there something that could tell me what the normal force is? Normal force we found was equal to mg, so mg replaces our normal force where it was in the x equation. Does that make more sense? Perfect. This is a big part of why we love to draw these pictures, though, because when you look at a picture, you can say, okay, everything, I do like a scan line across. That's my x direction. I do another scan line vertical. I say, that's my y direction. And I just group everything I see in each of those lines together in one big equation together. All the x's, all the y's. All right. So, let's imagine a scenario. Let's get a little bit funky with it. Let's imagine an alternate universe where perhaps Bonnie has taken a physics course before and knows a thing or two about how friction works. Let's imagine we're in a very much the same scenario, except in this universe, Bonnie had decided to pull at a slight angle up from horizontal on that rope. 20 degrees above the horizontal, to be exact. But still, this is an alternate universe. This is not the same scenario that we just looked at. The coefficient with the floor is no longer 0.25. It is some other mystery number. If Bonnie had decided to pull up by 20 degrees, but we still move at a constant speed, what would the coefficient of kinetic friction be now? So, draw a new picture, because one of our forces has changed, and I just get some practice with those free body diagrams. I promise it'll pay off. Look at this one. It's going to follow very much the same steps as before, but now, because one of those forces is no longer pointing in the x or y direction, it's pointing in between somewhere, we need to be a little bit more careful with how we deal with summing up all of our y forces, all of our x forces. One of them is going to show up in both. So, take another 4, 5, 6 minutes to work on this one, and then let's come back together and take a look. All right, so let's start taking a look here. And I said, please, 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 please draw a new picture because it's worth the practice. But I'm going to copy one because I have had my practice at this point, and I'm going to see a very similar picture to what we've just had here. So let's take that entire thing, let's move it over somewhere, move it all the way down here, and now we need to look at what has changed between these two scenarios. Bonnie's force no longer pulls directly horizontal. So get that out of here. Has anything else changed that I need to get rid of and change? Or do we feel comfortable with what we see now? Or are about to see, I guess. Has friction changed? Has our velocity changed? Anything else? Or are we comfortable with saying that everything's the same? Do a dotted line right there. Something like that. And I'm going to say this is probably the only change we would expect to see. We've just got this angle theta here now. So, now with all of these things, we're still given all of the old details that we had from before as well. That is, the mass, still 300 kilograms. The force from Bonnie, still 350 newtons. Now, it just comes with this extra theta of 20 degrees. Force from Clyde, still 385. The acceleration, still 0. Okay. Still asked to find the coefficient of friction. So I'm going to take the exact same approach as last time. I'm going to start by thinking about every single y component. All of the forces acting on this thing, sum up all of the y components. Because when I sum all of them up, because the net acceleration is 0, I expect the net force to be 0. I expect the force in the y direction to be 0. We have the normal force, same deal as last time. We have gravity, same deal as last time. We have a new one. This right here is not just pointing in the x direction anymore. This is now also pointing in the y direction. And because of that, it finds its place in our y forces. Is it going to be sine or cosine? I would agree sine, but let me check it just in case. If theta were to be 0, I would be going back up to my old picture. If theta were 0, f of b would point exclusively in the x direction. There would not be any part of it in y. Sine of 0 is 0. That matches with my description. X is going to get the cosine. There's my complete expression for everything in the y direction. Let me do the exact same thing for the x direction. X direction, we're supposed to have, well, still 0, right? We're still in a dynamic equilibrium. We have Clyde's force. We have the x component of Bonnie's force. And we still have friction. Same deal as last time. Let me plug in what I know about kinetic friction. Mu of k times the normal force. I cannot just plug in mg for the normal force. Do not do that. It will be wrong. If we go back up to our y equation, well, first of all, let's go ahead and highlight, say, hey, we're looking for this. Hey, we don't know this. Remember, the normal force is a reactive kind of force. It is only there to stop the objects from pressing into each other. If somebody starts to lift up, the floor doesn't need to provide as much normal force to stop the safe from falling through the floor. So I go back up to my y equation, I say, okay, well, I know f of b, I know theta, I know m, and g is just a constant. Let me rearrange everything to find that the normal force should now be equal to mg minus fb sine of theta. That is, as Bonnie pulls up more and more and more, the floor needs to do less to continue to lift the rest of that. So these are the things that we've got. Now, our new and improved expression for the normal force is going to get plugged in down here. Same deal as before. Fc plus Fb cosine of theta minus, now this expression is going to get a little bit obnoxious, mu of k times mg minus Fb cosine of theta, Fb sine of theta, sorry. That whole messy thing. But that's okay, that's not the craziest thing in the world, because if we look at this, the only thing that we don't know now is mu of k. We're ready to solve. And remember that the other side of this is still equal to 0. So I'm first going to move over my mu k term. Right, the physics is over. Now we're just doing some algebra. Now that we've got this, divide over by this whole nasty expression. For our final answer, mu of k is Fc plus Fb cosine of theta divided by mg minus Fb sine of theta. And it looks a little bit different from our last answer, but not wholly different, right? Fb plus Fc, yeah, we still see something like that. Divided by mg, yeah, we still see something like that. If we had decided to plug in that theta is equal to 0, so that we recreate our last problem, I would indeed get the exact same expression back out. Cosine of 0 would become 1. Sine of 0 would become 0. We get our exact expression that we had found from before. So plug in all of those numbers together, and you should end up with a final value now of 0.253, which, let's think about what that means for a second here. That means that the friction coefficient would have to be higher. There would have to be more friction from the floor to compensate for the fact that somebody's lifting. This is a furniture moving tactic. That is to say, if you're trying to slide something across the floor, your best bet is to lift a little bit. Don't push down on the box and try and slide it across the floor. You're going to make yourself do more work. At the very least, push it horizontally. But if you can, try to lift a little bit too. FB cotangent of theta? No, you would not, because each of these, top and bottom, are both in a polynomial. Not unless you did some real wacky stuff. That's about as simple as you can get it right here. All right. I've got one last one here. And this is, this one's for all the marbles here. I have a purely symbolic problem, and I hear the shouts of joy. Yes, we love symbolic problem practice. Yes, it's not too abstract. It's very understandable exactly as is. I know. But this is fantastic practice. I do promise that. Let's imagine here that we have an object of mass m at rest on top of a straight slope, height h, hypotenuse L. The coefficient of friction, of kinetic friction specifically, between the object and the surface is mu of k, and it's small enough that if it's sitting perched right at the top of this thing, all we need to do is give it like a light bop. Sends it's on its way. So there's no sort of applied force because we pushed on it. Let's assume that it starts from 0 velocity. We gave it just enough to get it moving and no more than that. So, knowing these variables, m, h, l, mu of k, and then g if you need it, which you do, sketch this thing out. Draw a good picture, label all the forces. Part B is seriously, draw the picture, label all the forces. Part C, find an expression for the object's speed, the final velocity at the bottom of the slope in terms of these other variables. What we're going to do here is we're going to spend the first 2, 3, 4 minutes making sure that you've got a good picture here. Get that picture right first. As soon as you're done with the picture, start tackling on part C. But at the end of those 3 or so minutes, I'm going to jump in, show you what I would draw for a picture, and make sure we're all on the same page. So, go ahead and get started with this thing, and I will interrupt you in just a little bit with a hand-drawn picture personally from me. Okay, so let's take a look at this thing. I want to make sure that we've all got a at least similar looking picture, so we're all on the right page for actually getting into this thing and solving it. So, first things first here, let's go ahead and draw this thing out. Let's do something. Here's like our big level ground as what level would be. Let's get our height, our slope, something like this. We have our block. Oh, not a square like that. That doesn't help you very much. Here's our block, right? And what do you know? It's a block on a slope. There's the joke again. Cue the laughter. So I'll label that. I'll label this. I'll label this. One of the things that I like to do with this as well is sometimes when I know that there's like a little bit of friction, a little bit of grit, then I'll add like a little bit of a, kind of like a fuzziness to it like this to say, hey, don't you forget, this is not a frictionless surface. This has some friction associated with it. It is rough. It is not particularly smooth. With that, you can label that mu sub k. All right. Now, let's think about the forces here. What forces do we have? List them off for me. Gravity, normal force, I would agree. Gravity pulls straight down because that's where the ground is, that's where the earth is. Normal force does not point straight up. It does not look like this. I'm going to wave my mouse around violently to say, no, not like this. Remember, a normal force always points perpendicularly away from the surface. Perpendicularly away from the slope. Not straight up, away from the slope. I'm looking for one more. What's the last one? Friction indeed. That surface is gritty. Oh, I can't draw that angle. Try it like this. This might make it a little bit easier for me. Oh, it's still terrible. A little bit more? Something like that. And the reason I know it goes like this, and let me talk about that a little bit, because if I go back to, or let me just draw this trajectory. I know this thing is going to slide down the slope. It's not going to launch off. It's not going to fall through the slope. It's going to go down the slope. If I were to draw what I would see all the way down here, here's kind of my final instance of the block, now falling into the floor or something. We know that there's going to be a final velocity going like this, down the slope. We have a trajectory of where this thing should be going, just like that. And I do a dotted line for this to say, hey, remember that this thing is going to travel down the slope kind of like this. So when I'm thinking about that, what should I pick for my axes? What do we think? Should I do my normal straight up and over axes, or should I tilt this thing? What's going to be easier? Tilted indeed. Because the normal force, the friction force, the final velocity are all on these tilted axes. So if they're all on these tilted axes, gravity's the only thing that stands out from that. Might as well make my life a little bit easier. I'm going to set my axes so they point like this, and they point like this. Off the slope, down the slope. With all of that in mind, here's my y, here's my x. My last little piece of advice. I am not given an angle. That is not one of my given variables, but wouldn't it be nice if we had one? Let's pretend for a little while. In your solving, label that theta. Go ahead. Make up a variable. It's fine. I won't tell anyone. Make up a variable and solve assuming you had theta. Then when we're done, we can go back and figure out some way to find it. So, focus finding this final velocity. Remember, if you're looking for these things, I can label out your givens here, but we're going to take the next 5 or so minutes, keep working, see if you can find an expression or get close to that final velocity. And then we're going to take a look at this thing together. Okay, so, because I know we are starting to butt up against the end of the class here, let's take a look at this thing, let's solve this thing out, and if you are most of the way there or something else like that, there might be a few key steps that we can talk about on the way there. So what I'm going to do with this thing is I'm going to say, okay, I know there is probably an acceleration, but that acceleration is not in the y direction, it's in the x direction. This thing is not flying off, it's not falling through. F of y should equal 0. Because I don't see any sort of movement in the y-axis, right? It's just sliding along the slope in the x-axis. So let me take all of the forces that I've got going in the y direction, which would be the normal force, and then the y component of gravity. So this one's a little bit trickier. Let's zoom way in on this thing, talk about how this split's going to happen. If you don't remember how the split has happened, or you haven't watched the lecture from last time, please, 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 go back and take a look at that. I've got a good description of how we exactly find this thing and we zoom out on it. But the summary is that we find that that angle right there is theta. So this is our f of y, this is our f of x from gravity. With all that information, f of y is which one, sine or cosine? Cosine in this case, exactly. And I think, again, if my angle goes to 0, if theta were to go to 0, if theta had gone to 0, then all of it would be pointed in the y direction. So that's the cosine. So let's go ahead and just write that out. mg cosine of theta. And that's it into the y direction. Now we look in the x direction. In the x direction, we start with 0 velocity, we end with some velocity. I expect there to be an acceleration. So let's not call it 0, let's say m times a. In my positive x direction, I have the x component of gravity, as we can see right there in the picture. So that's going to be my mg sine of theta. Resisting that is my friction force. And that's it. No other forces in the x. First things first, replace friction with what we know it to be. So that's mg sine of theta, same as before, minus mu times k times the normal force. I don't necessarily know what the normal force is, but I look at my y direction and say, hey, my normal force shows up right here. Normal force is mg cosine of theta. Plug it in. M times a of x should be equal then to mg sine of theta minus mu k mg cosine of theta. Cross out my m's, and I'm left with an expression for my acceleration in the x direction. G, I pull out the g to simplify this just a little bit more. Mu k cosine of theta, and that's it. Now, forces are done. Dynamics, over. Back to kinematics. Looking at what we've got here, we're looking for a final velocity. We have an initial velocity. Do we know anything about the time? I'm going to say probably not. I don't have any real information about the time, but I do know something about the distance. So if I'm looking for this final velocity, I really had two possibilities for which equation I might use. I've got that one, and I've got this one. And the problem with the top equation is that it doesn't include anything about the distance, but it does include something about time. Time is not something that I know about. But my delta x, looking at my picture, the distance traveled, that's my capital L. I have all of the variables I would need for the bottom equation, but I would have to solve out for time first if I wanted to use the top. Top equation is not the way I want to go. So we take this thing, we say, okay, well, we're looking for our final velocity. We know our initial velocity was 0. We know that delta x, whoops, black please. We know that delta x is actually just our capital L. So we're going to plug in our velocity as we have just found it, not our velocity, our acceleration as we have just found it into this expression right here. And we get something that resembles what we should have for a final answer here. Let me think here. 2 times L times this mess. And for our final trick out of the hat, the last thing that you would have to do for this one, and I can show this, but I want to make sure that I end actually, oh, I'm at 406. I have failed. It's going to say the last thing that I need to do is I have made up my angle theta, but I know that sine of theta, because I'm in a big triangle, SOHCAHTOA says that sine of theta is equal to the opposite side length over the hypotenuse. I can use this relationship to find theta. So, we're at past time at this point, though. I'm so sorry for that. But that is all I've got for today. Thank you so much for everyone for being here. I really do appreciate it. If we do have questions, I will work through the rest of this to show this thing, but I do want to close it out right there for anybody that needs to get on moving. Thanks for being here. Have a fantastic weekend. For an actual finish for this thing, if we are interested in seeing that. And thank you for being here. For an actual lesson for this thing, if we wanted to see the very end of this thing, what I would have to do is a little bit of extra trickery. I'd have to say, hey, this side length right here, I use Pythagorean theorem to say that this is L squared minus H squared, square root of that. That's what my last side length would be. So if sine of theta is H over L, cosine of theta is square root of L squared minus H squared divided by L. So a little bit of tricky trigonometry. But now both my sine and my cosine are in terms of things that I do know. And the reason that I really, really wanted to do that is because now I didn't have theta, but now I could have used theta this entire time because it was easy. And at the very end, when I'm all finished solving everything else, come up with an expression for theta. So in the end, our final expression would have been 2 times g. The L's would cancel out. I would have h minus mu k square root of L squared minus h squared. All of this under a square root, which I know is a little bit nasty, but that is a true final expression for this. Sorry for carrying over like that. You could do arcsine of h over L for theta, but then you would have cosine of arcsine of h over L. That's why I've tried to avoid that one. It does work, but it's a little bit nasty. Okay. Again, I'm so sorry for carrying over and everything else. That is the charm of mathematics indeed.